The mathematical methods that we take for granted today were not invented all at once. They were developed over many iterations, starting with some kind of simple method that was known to get the right result, and slowly giving rise to minor refinements over time, which made the more efficient systems that we take for granted today. Because they're so refined and efficient, the way that they actually work is somewhat hidden from view. One of the best examples of this is our long division algorithm, an algorithm which is very hard to understand. Like, why is it that you get to guess each digit at a time? Why do you put all of these digits in the particular place that you do? Why do we bring the particular digits down that we do? All of these questions will be answered today by going through that iterative process, by identifying the steps that someone could have taken during this refinement process to go from a simple long division algorithm to the streamlined, efficient algorithm we understand today. All of that is coming up here on Inductica. Motivation. Algamesh has invented a new number system. He's invented the number system that we take for granted today. And now he needs to make sure that this number system is able to do all of the different mathematical operations. And in this video, he's going to make sure that his number system can actually do long division. So this leads him to the following question. How can division be done reliably, easily, and quickly with Arabic numerals? Investigation. Algamesh starts by thinking that maybe he can use the same basic algorithm for long division as is used for Roman numerals. So that cites an earlier video, which you can see in the description. He's going to set up the following problem. 224 divided by 7. He's going to start by using the same basic idea that Roman numeral division is done in. He's going to write the problem out like this. We have 224 things, and we're trying to split those things into 7 equal groups. And the way to think about this is that we guess at how many things we can allocate to each of these 7 groups. And we're always going to want to guess low. And you'll see why in a moment. First, he's going to guess 15. So if you give all 7 groups 15 items, then you can ask how many items did you distribute overall? To find out, he's going to have to do 15 times 7. He's going to, of course, use a prior induction. That was our last video, Arabic numeral multiplication. Let's see him do that. So he does 7 times 5, that's 35 using his multiplication tables. Then 7 times 10, that's 70 using multiplication tables as well as the addition of zeros rules. These are things that were covered in our last video on multiplication. Then he adds all of these things up. 105. So he knows he's distributed 105 items so far. So what he's going to do is he's going to take 105 and he's going to subtract it from the total number to be distributed so far. And so now he's going to do Arabic numeral subtraction, which we covered in a prior video as well. So to do that subtraction, he's going to borrow, and there's 119 left. Okay, he notices something. He has 119 left to distribute, so he knows he can distribute to all 7 groups 15 more. And he already knows it's 105, so he just does this again. Kind of convenient. 9 minus 5 is 4. 1, 0. 14 is left. Okay, and he knows that 7 times 2 is 14, so he can give each group 2 more. He adds all of these things up, and that gives him 32. He can give each of the 7 groups 32 items. Okay, so he knows that in principle, he can use basically the same algorithm as he used with Roman numeral division, but he can just use it with his own number system. Over the course of using this algorithm, Algamesh is going to notice that he can refine the algorithm to make it a little faster and a little easier to use. Watch this. So he comes across another problem in the day-to-day use of his algorithm. He's going to do 357 divided by 3. Once again, he sets it up using the normal system. Once he does this, he's able to immediately see that 100 is a good guess. How does he know 100 is a good guess? Well, because he knows that 100 times 3 is going to give him 300. I'm going to skip the part where I do the actual multiplication to spare you. So it's 300. This is nice because he used the addition of zeros zeros rule, and this is part of what Algamesh discovered in our last video. So once again, you can see that prior video in the description if you want. He's used the addition of zeros rule. He knows that 1 times 3 is 3, but then there's 2 zeros here. So that means that the product is 3 followed by 2 zeros. He's using this rule to speed the process. He knows he's allowed to guess 100. We then do a subtraction. That subtraction is very easy. Then he looks at this again. He says, hey, I bet I could make a guess that's really similar to my last guess. He sees that there's a 5 here in the tens place. So he just says, well, what can I put in the tens place? He can't put 2 in the tens place because that's going to give 60, and this is smaller than 60. So what he does is he just guesses what's in the tens place. He knows it's going to be 10. He can distribute 10 more to everything. Why? Well, because 10 times 3 is 30, and that's the greatest set of 10 he's able to distribute to all 3 groups. That makes that quick. Then it comes out to 27, and he knows just from his multiplication tables that 3 times 9 is 27. So he adds all this up, and he gets a final quotient of 119. Quotient means the answer to a division problem. So this allows Algamesh to come to an intermediate conclusion that one can use the addition of zeros rule to make consistently appropriate guesses for these subquotients easily. Okay, now how did he do that? He knew that 100 was an appropriate guess because 100 times 3 is 300. It accounts for that. Then 10 times 3 is 30, which accounts for as much of this as he can. And so there's this way of guessing each of these efficiently. In this next problem, Algamesh is going to refine his method even further using some of these intermediate conclusions he's already reached. And he's going to do the problem 49,136 divided by 12. Once again, he writes the problem out in the usual algorithm. What he's going to do is he's realized that he can always think about the specific places in the quotient and ask what digit is going to go in that particular place of the quotient. Let's think about how that works. And the reason this works is because of the addition of zeros rule. He asks himself, is there going to be some number in the 10,000s place of the quotient? This place right here I've circled. Well, any number he puts here implicitly has 4 zeros in it. So the real question is there anything that you can multiply by 12 to get 4? You can't. There's nothing you can multiply by 12 to get 4. So there's going to be nothing in the 10,000s place. This leads Algamesh to an intermediate conclusion. Whenever a digit in the quotient would multiply with the divisor to a number which is greater than the amount to be distributed, then there is a 0 in that place. And just a reminder, the divisor is the number we are dividing by. So what's Algamesh's next step? Next, he's going to ask himself, I can't multiply anything by 12 to get 4, but is there something I can put in the thousands place to try and get 49 thousands? Well, yes, of course. I can put a 4 here. Okay, now why is a 4 okay? He does 4 times 12, although really this is 4,000 times 12. And that gives, it doesn't give 45, 4,000 times 12, which is 48, but really it's 48,000. Notice he doesn't have to write these zeros though, because simply being in this place or in this place represents 1,000s, 48,000s, or 4,000s. So he knows there's just a 48 here. This allows Algamesh to come to an intermediate conclusion. Whenever a digit is guessed for a given place value of the quotient, that will be the highest digit that will appear in that place value, so long as a higher digit would exceed the remaining dividend. So what does that look like in this case? What that means is that 4 in the thousands place got us to 48,000. It means we distributed 48,000. A 5 here would have distributed more than the overall quotient. And so as a result, we know that this is the greatest quantity that's actually going to end up in that place value. This is what allows us to go one place value at a time. Now he can subtract and only consider these first two leading decimals. Notice it's the same system, but since he knows that all of these are just zeros, he doesn't have to think about them. We're uncovering how the modern algorithm works. Subtraction is done, 1 is left over, or 1,000, and then the next thing he does is he simply moves this 1 down here. Why does he move a 1 down here? Really, it's 100. And the reason is this: his next guess is going to be in the hundreds place. Something in the hundreds place times something in the tens place is going to give us something in the thousands place, something that can cancel this number that I've circled right here. Then something in the hundreds place multiplied by something in the ones place will give something at least in the hundreds place, which is going to be able to cancel this number right here. So he's only bringing in digits from the dividend that are needed to actually conduct the next guess for the next place value of the quotient. Now, just a reminder, the dividend is the number we are dividing up. So now he's going to guess, once again, he's guessing what's going to be in the hundreds place. And he asks himself, well, what can I multiply in the hundreds place by 12 to get 1100? Well, as soon as we multiply some number of hundreds by 12, that's going to give us 1200 at least, and that is greater than this, which is only 1100. So there's going to be 0 in that place value. Look, there's already a 0. I'll make it look more like a 0 rather than a circling comma there, because that 4 is the thousandths place. Now that he knows that this place of the quotient has to be 0, he's going to bring down another number from the quotient. He's now going to guess the tens place of the quotient. And this tens place of the quotient is going to multiply with this 10 to produce 100, which will account for this space, which can cancel out with this space. And this space can also multiply by the ones place, which will produce some number of tens. So that allows us to cancel this space. So we need something in the tens place to actually cancel with. Again, this is doing a minimum amount of writing. It's a little complicated to understand though, which is why I'm breaking this down. All right. So he's now going to guess, what number can I put here? Multiply it by 12 to get 113. Maybe he guesses 8. He tries that. 8 times 12 is 92. Let's say he works that out. He does the subtraction, and he gets 21. 21 is left over. Here's the thing, 21 can still fit another 12 into it. So he actually knows he guessed too low. At any stage of the process, if you subtract off and you get a number that's less than the divisor, then you know you've guessed too low, because you know that 21 tens remains, and you could have multiplied 12 by some greater number of tens to chop more of those off. So he's going to guess 9 this time. Let's try 9, and then he'll erase all of this. 9 times 12, he does the multiplication. I'm sparing you that part, is 108. Does the subtraction. This comes out to 5. Again, sparing you the process. Finally, he's going to bring down this 6. And why is that? Once again, it's kind of the same logic as before. We're now multiplying by some number of ones. A number of ones multiplied by this produces some number of tens. That's able to cancel with this. A number of ones multiplied by a number of ones produces at least some number of ones, which is able to cancel with this. So we need to bring this down into the remaining number to be distributed so that we can guess this final place of the quotient. He then guesses 4. Does the multiplication. 4 times 12 is 48. Does the subtraction to find out how much is left. That's 8. 8 cannot be distributed evenly among 12. And so the final answer is 4,094, remainder 8. Conclusion. To divide with Arabic numerals, identify the quotient one digit at a time based on the addition of zeros rule. Once each digit of the quotient is identified, multiply that number by the divisor. Subtract the resulting product from the dividend to find the new dividend. Include digits from the original dividend in each new dividend only as needed to simplify the process. Repeat this process until each digit of the quotient has been identified. Any amount left over that cannot be divided equally is allocated to the remainder. In the modern division algorithm, we identify the quotient one place value at a time. And now we can see how that was made possible. It was made possible by this iterative line of reasoning. It started with the basic Roman algorithm where Algamesh simply guesses part of the quotient, multiplies, then finds out how much he has to distribute. Then he realizes that he can use the addition of zeros rule to make better guesses. After a while, these better guesses led Algamesh to realize that he was able to make a guess for each place value, and that once he made that guess for the place value, that's the place value that would be in the final quotient. So through this iterative process, Algamesh was able to streamline a clunky system of long division into a very streamlined, efficient system for long division, considering only one part of the quotient at a time and guessing the place values of it. So now Algamesh has fully developed Arabic arithmetic. He has identified all of the basic operations for using our modern number system. Join us in our next video as our next hero invents a system for dealing with partial units. I'll see you then. This video is part of a longer series dedicated to reproving the essential ideas of math and physics by showing an actual process of observation and reasoning steps scientists could have taken to prove these conclusions. Observational proofs, also known as inductive proofs, give us a deeper, reality-based understanding of these abstract ideas and demonstrate the proper method of scientific proof. This series starts with cavemen counting rocks and will continue all the way to the frontiers of quantum and relativistic phenomena. This epic story will proceed in a possible order of discovery, since science always progresses by reasoning about observations using what has been discovered earlier. To discover the long-term goal and the true power of this project, visit my channel page for more information. To see the playlist for this series or to see my channel, just click on the links on the screen. Finally, if you'd like more lectures like this, just go to patreon.com/Inductica. For just $5 a month, you gain access to the written, rigorous forms of these proofs, as well as my 34-hour lecture series and inductive summary of physics. I'll see you in the next video as this inductive journey continues.